Hello everyone and welcome to this Merge Talk presentation. My name is Obada Alia and I'm a PhD student at the High Performance Networking Group at the University of Bristol. In the first half of this presentation, I'm going to talk about the coexistence of quantum and classical channels over hollow core-nested anti-resonant nodeless fiber. The vision behind this work is the quest for a reliable seamless coexistence medium in which we can coexist the quantum channel with high-power classical channels with a minimal effect on the quantum channel performance. For applications such as quantum key distribution and distributed quantum computings, the quantum channels are usually used to distribute the quantum state, such as a polarized entangled photons, whereas the classical channels are used to exchange measured information about these states. However, using separate multiple fibers for quantum channels and classical channels would be extremely impractical for large-scale quantum entangled networks. So far, coexistence has been implemented using single-mode fiber only, which limits the coexistence due to two factors. The first factor is the nonlinear effects in single-mode fiber such as Raman scattering and four-wave mixing. The second factor is the loss of 0.20 dB per kilometer, which was achieved back in 1979. We believe hollow core fiber provides us an alternative and, in fact, the ultimate medium for quantum and classical coexistence. Since the light travels in a hollow core, it has ultra-low latency, ultra-low nonlinear effects, flat and low chromatic dispersion, which are very important features in the coexistence of quantum and classical channels. It also has the potential of having an extremely low loss, 10 times lower than a single-mode fiber. Coexisting discrete variable quantum key distribution system with the classical channels present a great challenge. Since the QKD system is a single photon transmission system, where typically the transmitter transmits at around -70 dBm and the receiver sensitivity is around -90 dBm, the system is extremely sensitive to noise photons within the time window of the receiver and within the optical filter bandwidth of the receiver, which means very high extension bandpass filters are required for both the quantum and the classical channels, since the quantum signal is around 60 to 80 dB lower power than the classical signal. Moreover, these systems are highly sensitive to Raman scattering, and the single photon cannot be amplified. In this slide, I'm showing the progress of NAND fiber over the last 6 years. As we can see, the loss of the fiber went down from 200 dB per kilometer in 2015 to around 0.28 dB per kilometer in 2020. I'm going to be mainly focusing on the last 3 fibers in here, made by the ORC, the Optical Research Center, Optoelectronics Research Center at the University of Southampton. The first fiber here has a loss of 1.13 dB per kilometer and is used for this experiment. The second fiber has a loss of 0.65 dB per kilometer, and these two fibers are compared in the next slides. The last fiber has a loss of 0.28 dB per kilometer. The top right figure shows us the improvement of the loss if we increase the size of the core. As we can see, if we increase the size of the core at around 50 micrometer, the losses will be around 10 times lower than the single mode fiber. And this simulation is important because if we look at the bottom right figure, the red line shows us the experimental loss and the black line shows us the simulated loss. And as we can see, between the 1500 and the 1700 nanometer, the losses exactly match, which means one day we could have a fiber that is 10 times, the losses is 10 times lower than the single mode fiber. In this slide on the left here, I'm comparing between the 2018 and the 2019 fiber. As you can see, the 2019 fiber has a bigger core and a thinner membrane. Therefore, it has much lower losses than the 2018 fiber. Also, if we look at the red line, which is the measured loss, and the black line is the simulated loss, between the 1500 and the 1750 nanometer, they have exactly matching loss. The middle figure in here shows us the confinement loss of the different modes in the fiber. As we can see, the fundamental mode has a 0.27 dB per kilometer loss, whereas LB11 mode has a loss between 6 to 10 dBs per kilometer. LB21 mode and LB22 mode has an extremely high loss of 5000 dBs per kilometer, since these modes are phase matched with the cladding modes, giving them this extremely high loss. At the ORC in this year, they improved the design by using 5 nested tubes. These 5 nested tubes gives us a bigger core and more spacing in the cladding. Therefore, we can see that the LB11 mode in the 5 node increased from 6 to 10 dBs per kilometer in the 6 node to around 2500 dBs per kilometer, providing a single moded hollow core fiber. Here is the experimental setup used to coexist quantum and classical channels. For the classical channels, a bandwidth variable transponder switch is deployed to transmit 4 coherent classical channels, whereas for the quantum channel, ID-Contig Clavis 3 QKD devices that implements the coherent one-way, also known as COW protocol, is used. The 4 coherent output ports from the VVT are multiplexed using a wavelength selective switch. We used a WSS as a multiplexer and the bandpass filter to provide a 30 dB isolation in the first stage of the filtering. The output of the WSS is fed into the input of a tunable bandpass filter with extremely sharp edges that provides us 60 dB of isolation. These 2 stages are required to suppress the noise generated by the classical channels. The classical channels and the quantum channels are then coupled through a WDM multiplexer in a coexisting configuration and travels through 2 km of either multi-core fiber or hollow core fiber to a WDM multiplexer. This WDM multiplexer passes the quantum channel to the Bob receiving unit of the QKD and rejects the classical channels to an optical isolator. This optical isolator is used here to prevent the ASE noise from the erbium dome fiber amplifier of traveling back to the Bob QKD unit to alter the measurements, but it also prevents the tunable lasers that are used as local oscillators for coherent detection from the VVT RX of traveling back to the system. After the isolator, the classical channels are amplified and then splitted into 4 different channels for the coherent detection. This is the picture, a cross-sectional diagram of the multi-core fiber, and this is the cross-sectional diagram of the 2018 ORC hollow core fiber that was used in this experiment. The losses of the quantum channel is 10.5 dBs from Alice all the way to Bob, and the classical channels are used in this experiment are 100G BMQPSK. This figure shows us the quantum channel performance using the multi-core fiber. As we expected, when we increase the number of channel and increase the power, the performance of the QKD the secret key rate goes down as expected, due to the high leakage of noise photons in the Bob detector. However, when we use the hollow core fiber, when we increase the number of channels and increase the power, there is a very minimum effect on the secret key rate, which is around 10% in this experiment. This shows us that the ultra-low nonlinear effects in the hollow core fiber are extremely different from the multi-core fiber that use single mode fiber, basically. Here we can see around 90% decrease in the secret key rate, whereas here at the maximum power we see around 10% decrease in the secret key rate. This slide shows us the coexistence of 8 classical channels in the hollow core and single mode fiber. This work was submitted in ECOG. As we can see, at -9 dBm coexistence power per channel, which means 0 dBm coexistence power when we have 8 channels, the classical channel performance went down around 5% only. Whereas in the single mode fiber, when we use a power at -16 dBm, which is 40 times lower than the power used in hollow core fiber, the performance goes down around 87.5%. Although the power is much higher in here, the ultra-low nonlinear effects shows us the superiority of using hollow core fiber for coexistence. This is the end of my talk, and there are a few points that I would like you to leave with. If we would like to use the quantum technology with the classical optical networking infrastructure is extremely important to be able to integrate them together in a coexistence configuration. We just showed that hollow core fiber can achieve ultra low latency, extremely low nonlinearities, and low and flat chromatic dispersion because of the hollow core. Therefore, if the losses goes down to a good level, and so far we saw that it went down from around 150 dBs per kilometer to 0.22 dBs per kilometer this year, we are on the right path. Experimental results proves that using the hollow core fiber for quantum classical coexistence is much better than single mode fiber, even though the power in the hollow core fiber was 40 times higher than the power used in single mode fiber. The secret key rate was preserved in the hollow core fiber, whereas in the single mode fiber it went down to 87.5%. I would like to thank everyone that was part of this work, and I would like to thank all our sponsors. And now I'm going to leave you to the second part of this talk with Fadri. Thanks a lot.
Hello and welcome to the second part of this merged talk. My name is Fadri Grünenfelder and I'm a PhD student at the University of Geneva. I will talk about the limits of multiplexing of quantum and classical channels, and we will look at a case study of a 2.5 GHz QKD system we implemented in our lab. So how do we integrate QKD systems into a network? For this, we quickly look at an example as shown here. So we have two nodes of a network. They are connected with two fibers. One fiber carries communication in this direction, and the other fiber carries communication in the other direction. If now Alice wants to share a secret key with Bob, she chooses a wavelength which is not yet used in the network and couples it into the fiber such that the quantum signal and the classical channels are co-propagating. Bob, on the other side, just demultiplexes the wavelength and measures the arriving quantum signal. However, there is a small problem, and that is that we have some network components where we can't travel through with our quantum signal, for example, amplifiers. And to solve this, we just couple out the wavelengths, circumvent them, and couple in again. And now we can ask, what is the maximum classical launch power which can be tolerated experimentally and theoretically in such a network, and which quantum channel wavelength is suited best for such an experiment. And for this, we quickly revisit Raman scattering, which is the dominant source of noise for QKD in a network. And the question we want to answer is the following. So if we have the network node sending a lot of classical communication at around 1550, which wavelength should we choose for our quantum setup? And to answer this question, we can look at some previous study where they measured the Raman noise. First, they measured it in the quantum channel at around 1550, while the classical light was also around 1550, and they did the same for quantum channel at 1310. And we can see that the Raman noise at 1310 is about 2 orders of magnitude lower than at 1550. Question is now, is it worth to use a wavelength of 1310, although it has a higher loss in the fibers of the network, or is it worth to use 1550? And the answer is, it is worth to use 1310, at least for short fibers or for shorter distances. For example, here we can see 50 kilometer single mode fiber simulation of the secret key rate. And we can see that already the quite low launch power, 1310 performs better than 1550. So in conclusion, we can say 1310 is better suited for short network distances. And this is also what we are using in our experiment. So now to what we are doing in the lab. So we implement the QKD system, which uses a 3-state BB84 protocol with one decoy. And it uses time-bin encoding. So it prepares the 6 states you can see here in the following way. So we have a 2.5 gigahertz gain switched laser at 1310 nanometers, creating pulses like this, which travel through a Michelson interferometer, which is unbalanced. So it will create pulses like this at the output. Then we use an intensity modulator to create our states and our decoys. And we send them to Bob. Bob uses the same or similar Michelson interferometer as Alice has to interfere the states of the X basis. So this detector measures the X basis state, and for the Z basis, we just measure the time of arrival. And Alice key characteristics I already mentioned. It's a 2.5 gigahertz qubit repetition rate, which is very fast. And we have wavelength at 1310 nanometers. On Bob's side, we use negative feedback avalanche photodiodes. The reason why we use them and not the superconducting nanowire single photon detectors is because it's more practical and it's cheaper. So if you want to have a widespread QKD solution, this is probably the way to go. Now let me quickly explain how the QKD gets integrated into the network. So we have the QKD system of Alice here and Bob here. And together with 13 channels, which are all around 1550 nanometers and different wavelengths, they got coupled into the same fiber, and then they get multiplexed together with the quantum channel. And then we send everything either through 95.5 kilometer single mode fiber, which has a loss of 34.8 dB at 1310. Or we send it through a 51.5 kilometer long fiber, which has some additional attenuation in between, which we consider more realistic in a network because we have a lot of additional components in a network or connections which are not perfect. And also this link has almost the same loss as a single mode fiber. And on Bob's side, we just split up the classical communication and the quantum channel, and we use a cascade of filters to have only a really spectral narrow region open at Bob's side, so that we really filter out a lot of Raman noise as well. The problem here is all these filters obviously come with a price. So we have a filter insertion loss in total with all the filters together of 7.2 dB. And additionally, because our laser is switched quite fast, we have losses of 1.9 dB due to pulse broadening, which happens in the fiber break rating, which itself is also slightly chirped, and due to the detector jitter. So our 2.5 gigahertz repetition rate is on one side an advantage because we have a higher signal rate, and also we can use commercial filters which are close to the bandwidth of the laser. If you would use lower repetition rates, then the spectral width of the pulse of the laser pulse would be lower, so we would need narrower filters which are not so commercially available. But on the other side, we have the problem of the chirp of the laser, which also comes from the fast gain switching, which gives us additional losses. Now, with the setup I just presented, we can do a secret key rate exchange. So we exchange secret keys over this 95.5 kilometer single mode fiber, and we reached 8.9 dB of co-propagating classical launch power. And we can do the same with the 51.5 kilometer channel together with the attenuation. And here's the interesting thing to note is that if the classical channels are off, the secret key rates are almost the same in the two channels. But if we turn on the classical channels, it turns out that for the channel with the attenuation, we can go to 16.7 dBm instead of only 8.9. And the reason for this is that the attenuation, the additional attenuation, has the same loss, or roughly the same loss for 1550 and 1310, which is obviously not the case for the single mode fiber. And now to give some perspective, I quickly compare our results to the literature. So on one side, we have continuous variable systems, which operate normally at 1550 nanometers. They are really good in terms of launch power they can tolerate, and they can create a quite high secret key rates, but only at quite short distances. For discrete variable systems which use 1550 nanometers, it's easy to go to long distance, but they can't tolerate a lot of launch power because of the increased Raman noise. For discrete variable systems at 1310, they usually perform quite well in terms of tolerable launch power. However, no experiment was performed at a distance as long as in our case. As you can see here, for different network environments, maybe different systems might be optimal. And with this, I want to conclude. So we could show that we can distribute a secret key up to a distance of 95.5 kilometers with our system, while we have co-propagating classical signals at a power of up to 8.9 dBm. Additionally, we can say that discrete variable QKD systems at 1310 have an advantage in short and medium ranged links compared to systems operating at 1550 nanometers, which is especially important in metropolitan area networks where the distance usually are smaller than 100 kilometers. Additionally, we also concluded something else which I didn't discuss too much so far. Namely, we simulated how an ideal system would behave, similar to the system we have in our lab, but with ideal detectors, with ideal laser pulse shapes and filter which match these laser pulses spectrally really well. And it turns out that we could go up to 27 dBm launch power at the same distance. And obviously this is the upper bound you can reach with such a system. And with this, I want to thank you for your attention, and I'm looking forward to nice discussions in the question and answer session.